Hello and welcome. Here we are in lecture 17 in the midst of our discussion of physical design issues. Last time we talked about things like latency and delay. Today we're going to talk about power and conclude that process. And then we're going to shift gears to the next topic about design space exploration. Let's go ahead and do that. So, as mentioned, we're going to talk about power and then talk about DSE or design space exploration. So, why are we talking about power? Well, for many hardware design scenarios, it's not just important, it's actually the most important thing for power design. For a long time, we've been able to build chips that are really, really fast, but we can't build them, not because they can't go that fast, but because they'll burn themselves up, right? That's been a scenario since basically the last 20 years. And so for most designs, we are power limited. Now, there's an issue of how much power you can extract to save, the heat out to keep from overheating itself. There's also an issue of just how much energy it takes in total, right, when it comes to the energy bill. So, of course, in mobile devices, the amount of energy sets to both the battery life and the battery size. Those are very impactful details. But also for physical things, right? Of course, if I have a chip plugged into a data center, you care a lot about how much power it takes because how much power you need to provision, all the infrastructure you need to put in place to support that, all the infrastructure you need in place to cool that, et cetera, right? And so it's actually a serious problem, even for mobile devices. You'd be surprised how even for a smartphone, the chips inside here, people are running hot enough where the phone can get too hot for your hand. You won't want to hold it anymore. And so to kind of recognize what's going to happen and throttle it and actually slow it down to keep it from happening. So power really is an important thing to keep an eye on. And so as a result, when we're talking about this as designers, we want to keep an eye on it and make sure we are matching things. And then it also impacts cost, like I said earlier, where whatever your power level is, you need to build infrastructure, supply that amount of power, right? You have to have all the passives and power supplies, voltage regulators, et cetera, supply that amount of power, or larger scale, your various, PDUs, those kind of things to supply that, and then you got to be able to cool that. That allows the cost. If you make your thing take less power, you can have a smaller power supply, cheaper power supply, etc. Makes everybody else happy. Okay, so uh, what's involved in power? Uh, there are a few things involved in power. The one we as designers are often most conscious of is something called dynamic power, which is the portion that is very much dependent on what you're actually doing in your circuit. And so here's an equation. You may remember this from, an architecture class, something like that. Power is proportional to this CV squared F. There's also, of course, this alpha, this activity factor. But it kind of makes a little bit of sense, right? In other words, if your circuit's largely inactive, you have a low activity factor. Okay, it's going to linearly scale down your power consumption. All right. Your capacitance, how much you're switching, that's going to change your power. And the voltage. And you notice how the voltage is squared, right? So voltage, you turn it down just a little bit, it's a huge change in the power, right? So that's one of those opportunities you can just have to really get a big gain. And then, of course, the frequency, right? If you run at half the frequency, you're going to burn half the power because you're doing half the charges and discharges per second. Um, this kind of thing. So when we talk about power optimization, usually you're kind of looking at all these terms independently. Or for example, architecturally, if you're able to figure out how to make your design, um, toggle less, well, that's the activity factor. Perhaps you're turning off portions of your design. That's less switching, right? It's the C factor. If you figure out how to improve your critical path, like we talked about last time, well, if you can reduce your critical path, you can achieve the same frequency at a lower voltage, right? You need less power to get there. And so that can, of course, get squared, improvements on voltage. Or perhaps architecturally, you can make your design take fewer cycles, in which case you can run at a lower frequency and get a lot of improvement there. And so you can kind of attack any one of these, right? When it comes to power. Cool. Questions, comments so far? Okay. Um, so as mentioned, when it comes time to save power in your design process, well, you want to turn things off, right? And so um, there's two kinds of things you can turn off, right? There's what they call power gating and clock gating. So power gating is, as the name implies, you cut the power to that entire portion. Say, hey, this is a portion of my circuit, this, this unit, this module, this IP block. I know I'm not going to use it for a while, so I might as well go ahead and just cut its power. And since I'm not sending any power there, it's not burning any power. It saves a lot of power. What's the trade-off here? Well, first of all, you have to have the ability to cut the power off this component. That's like some circuitry required for that. You also need to artificially have a design which can recognize the opportunity for this, and then have the ability to kind of turn this component on. And then when you turn it back on, resynchronize, reconnect to the rest of your design, right? So sometimes turning things back on, there's some sort of latency penalty. But if you turn it off for long enough, this whole thing is worthwhile. Meanwhile, there's clock gating. We don't actually turn off the power, you just turn off the clock. And the reason why is the clock is constantly toggling every cycle, right? It actually goes, 1 0 1 0. It's actually changes twice per cycle, right? So it's actually a very active component. And for clocked components, these are typically registers. The clock constantly toggling is using a lot of energy, right? And so if you're able to turn the clock off the components, you can save that clock power. Now, when you turn the clock off? Well, typically you can turn the clock off if you have registers that you know that you aren't intending to change the value of them. And so doing this for a single bit's not worth it. But if you have like a 32 64-bit register, yeah, you can recognize, oh wait, this register is not going to change. I can kill the clock to 64 bits of register, and that'll actually save quite a bit. And so what's interesting about this idea is optimization was pioneered, in the early 90s. There was tools doing it semi-automatically in the early 2000s. Now in 2023, if you're running an ASIC design flow, tools are extremely good at this. They'll recognize how to attach, the right enabled registers to clock gating to like turn it off on its own. Now the catch to that is you need the right enabling registers. So if you have just a vanilla register, which always takes input and always changes its value, well, the tools can't infer just something can turn it off. It doesn't know it can turn it off, right? And so as a designer, you actually need to use a reg enable, which has the right enable in it, and that's actually give the tools the possibility of doing this. Because one of the things that comes up with tools is often they can do really amazing things as long as they don't change semantics. In this case, the regular register, which has basically the enable always set to true, doesn't give tools enough freedom to kind of do what they want to do. In this case, you have a right enabled register. The tools can do this. So if you actually go through some designs, for example, like Rocket Chip, that big RISC-V processor, you'll find that not a register is a reg enable, but a lot of registers are a reg enable. And you think, well, why does it matter? It's for power. Because there's situations where sometimes the value of the register is a don't care. And so times when it's a don't care, if instead you have a register right enable and turn it off, you don't spend power on it once you don't care, as opposed to just having a don't care value and passing it around. And so these are kind of these small things. We start trying to optimize for power, these kind of things come up. Cool. Questions on that? Cool. Okay. So then these are a bit more architectural in concept, but when it comes to trying to save power, or I should say energy, excuse me, reminding folks, power is the instantaneous, draw of energy is power over time. You have two choices, right? Okay, of course you want to reduce your energy consumption, and there's kind of two philosophies. So one is, this is a very common one, is you want to go slow, right? Okay, you have some sort of goal you want to meet, or some sort of performance target. For example, if you're trying to play video, you need to make sure you render every frame in time for next frame according to either 30 or 60 frames per second or something like that. And so typically you have enough computational power to get the task done in time. And so instead you want to recognize, what, hey, this is a video frame. I have, let's say I have 30 FPS. Well, that means I have, 33 milliseconds to render it. So yeah, I can slow down the clock of my processor, and so I render it in 33 milliseconds, right? Rather than taking, 5 milliseconds to sitting around doing nothing. No. I'm going to slow down the clock. And remember, because you can turn down the frequency, when you turn down the frequency, you also can turn down the voltage. And because voltage is squared, you can get a huge energy saving, right? So this is a very standard practice. So processors often do this. Usually they said they change the frequency and the voltage together. This is called DVFS, for dynamic frequency, voltage and frequency scaling. A lot of processors also just do DFS, right? They're simpler, just frequency scaling. You get a linear saving in power. That's still nice. But normally, if you also change the voltage, you're getting bigger savings. This is common not just on laptop server class processors, but it's 100% required for something like a mobile processor, right? And you may have seen in the last few years, there's been a push for a lot of mobile designs, even laptop designs now, what they call big little, big cores and small cores. This is actually that kind of playing out, where they have cores that are designed for certain performance regimes, right? These big cores, of course, take more power, but they're deliver more performance. And if the workload demands it, they'll use those. If workload does not demand that, rather than slowing those at lower voltage, which they can do, they found these other smaller cores are better adapted to lower voltages and actually can perform more energy efficiently. And that's why they have both types of cores. But for today, the kind of key idea is, yes, we can slow down to go just as slow as we can to get our job done in time. And so we turn on the frequency, you can also turn on the voltage and get even greater energy savings. Sometimes folks call this crawl a deadline. It's kind of name for this. Okay, you kind of imagine just barely getting by the deadline. Cool. Question. Yes. Both. Yeah, yeah. So mobile devices, whether it be a laptop or a smartphone, for power saving, is it hardware or software's job? The answer is both working together. Um, so that's kind of the key thing. So this is one philosophy how to save power. This next slide is the other philosophy, and it turns out devices you use both, because you kind of need both working together. So the crawl to meet the deadline basically is okay. We're gonna figure out how to go slower because going slower is more energy efficient, right? It's also true driving a car, right? If you drive your car, typically if you're going 75 miles per hour on a freeway or whatever, that's actually not gonna be your best gas mileage, right? Depending on kind of car, maybe 35, 40 miles per hour tends to be the most efficient mileage because at that point you are experiencing less drag, and less drag is less wasted energy. And so same kind of thing. If you go slower, typically it's more efficient. So that's this one. This other approach is actually saying, you know what, slower is actually not good. It's actually better to go fast. You're like, wait, how does that make sense? Well, it depends on what kind of energy and power you're talking about. So the alternative to crawl a deadline is what they call race to halt, meaning you try to get your task done as soon as you can, and then you go to sleep. And so the whole point is that going to sleep is the key point. So even though you're burning more power and you're doing the task, because you can go fully to sleep, you can save power. And so to try to kind of visualize this difference, I made this diagram. So within your platform, your hardware design, there's two portions of power. There's your dynamic power, the one we spoke about earlier. There's also your static power, which is power that, when your thing is on, it just burns. And you change your frequency, it still burns the same amount of static power. It's kind of like, that unchangeable portion. So you kind of think of static power as the portion of power you can't change, dynamic power as the portion you can change. And so if you are able to race to halt, you have the ability to turn off the entire thing, and you get back the energy spent on static power. And so which of these is less energy? It's less area shaded. It depends, right? If you're a device that has a very low static power, then perhaps crawling deadline is more efficient because you're probably going to spend less on dynamic power. But if you have a device or a platform that has a lot of energy spent on static power, then perhaps it's better to race to halt to get that energy back. So that's kind of the point. So another way to think of this is crawl deadline is a way to save dynamic power, versus race to halt is a way to save static power, right? And the question is, which of those matters? And so like I said, depending on mobile devices, they do both. So earlier I gave you the example of, having a deadline for like a video frame and deciding, you know what, I'm going to go ahead and, go as slow as I can to meet that deadline. That's one option. The other option is to say, you know what, I know I'm going to render this one frame and nothing's going to happen until the next frame. I can go ahead and render this frame in a few milliseconds and put the processor to sleep 3 milliseconds until the next time. And so it turns out to have like a reasonable mobile battery life, you have to be really, 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 really good at sleeping a lot. And so to give you an example of how extreme it's gotten in the modern era, if you have your mobile phone, you think, oh, I'm looking at this web page and I'm browsing. If you're not actively scrolling, things are asleep. And what's even crazier, even when you think you're scrolling your phone on the screen, oh yeah, it's moving the page at 100 hertz, whatever it's moving at, 100 hertz, right? 10 milliseconds per frame. These processors can just sleep on a microsecond scale granularity if you need to, right? So they were definitely sleeping between what you're doing. And they have to. If they didn't do that, your battery life would be really, really bad. Also impressive on mobile devices. For something like either Wi-Fi or cellular signals, you often have a time negotiated when you're allowed to communicate. Okay, this is my time slot to negotiate. I've been told I can communicate. Otherwise, they'd be quiet, let people speak in the same radio spectrum. Well, guess what? If you know there's a time spectrum where you cannot be communicating, you might as well put your modem to sleep. And so they did. The modems go to sleep, the processor goes to sleep, they all sleep. So if you're doing a mobile device, you'd be really, 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 really good at sleeping. And so a lot of these sleeping conversations, it's about architecture. How do you make architecture turn things off, turn things on, turn things off, turn things on? And for this conversation today, I was kind of want to give you aware to these high-level trade-offs. And we discussed some of these circuit levels kind of tricks, right? Power gating and clock gating, right? So a lot of what I'm describing is power gating, which is the real big hitter. If you can do power gating, you get a lot of savings. But clock gating is one of these things where if you can do this, it kind of saves you energy all the time in these designs. So your design is just more efficient if you can do clock gating right. Um, there's additional tricks that are well beyond the scope of this course that I didn't cover. For example, one of the tools of synthesizing your design, which logic cells they use to choose to implement your design, of course, can change your power consumption, right? And so some technologies, for example, have multiple threshold voltages, and they can use slower but more power efficient gates off your critical path to save energy. Um, but that's beyond the scope of this course. But yeah, so going back to these kind of two trade-offs, these are kind of two philosophies. And so depending on the component you're looking at, you have a choice. And in practice, you do both for a lot of the time. And kind of deciding factor where you try and go as slow as you can or just race and sleep depends on how much static power there is. If there's a lot of static power, you really want to eliminate that and you want to go to sleep. But let's say in order to go faster, you might pay a premium in that energy, right? You might be paying more. Running at a higher frequency, higher voltage is squared. So it depends, right? You got to run the math and figure it out. Cool. Questions? Okay. So that's some of these power trips. I just want folks to be kind of aware of this kind of stuff. Let's shift gears and talk about design space exploration, or DSE, right? And so you're all experiencing this right now in your projects. And for many of you, you're excited to kind of get the thing working the first time, right? Which is an important, good first step. But you can imagine if you're, really trying to do a good job on a big project, you're gonna really ask yourself, okay, how do I know what the right design is, right? And so, okay, well, what's the right design? Well, what is right? How do you know what right is, right? And so naturally, you have to kind of figure out what your metrics are, right? So given a certain problem, a certain goal I'm trying to do, how am I going to compare different designs? Well, I need some sort of metrics to kind of evaluate them. And it becomes very apparent with these hardware designs that usually it's not just one metric, usually there's multiple metrics. There's multiple metrics subject to certain constraints, right? Some hard constraints, some soft constraints, et cetera. And so that's where this DSE comes interesting is you actually, well, turns out even if you have multiple metrics and you kind of highlight what you care about, there's still gonna be trade-offs, right? And if you come across an engineering situation, this is my own personal opinion, you come across an engineering situation and there's not trade-offs, that means you're not at the frontier. Like if something's just better than everything else, no matter what, that means you aren't giving it reasonable competition. Usually, in order to improve something, you gotta give something up. And we'll come back to this idea in a few minutes. But like, yeah, if you're making competitive designs, there has to be trade-offs. If there's not trade-offs, that means you're not at the frontier. Okay, so kind of given these constraints, what can we do? Well, first off, when it comes to hardware design, there's typically a zillion metrics possible, right? So we've talked a lot about PPA, power performance area. These are the knee-jerk response to most chip designers, right? So things like power, you consider, okay, what's my average power, which of course impacts your energy efficiency, or about your peak power, things like your heat profile and your power delivery requirements. Okay, performance we've talked about. You can imagine that's either an issue of latency versus throughput. Which matters for application. For some things involving users, you might care more about latency to kind of get very quick responsiveness to them, but maybe in data center you care more about throughput. How many inferences can you do per hour in your data center? And of course, there's cost. That's where area comes into this, right? It's like how big of a chip am I making, or how many I/O pins do I need? These other kind of things, right? So okay, so PPA are kind of the usual knee-jerk response is people have when they think about metrics, but that's only 3 on this list I made of what 8, 9, 8, right? So okay, at the entire system level point of view, there's a question of usability, right? Does this actually satisfy the application constraints, the application goals? Worth considering, worth talking about. In the modern era, of course, we're very concerned about security. Do you have side channels? Do you have backdoors? Do you have other vulnerabilities? Although it'd be nice to have, just send design off to manufacturer and be done with it, turns out not all hardware designs are equally manufacturable. So what your yield is when you actually manufacture your chips, that can vary. And you can change your design to make it more likely to actually have a high yield. So DFM, or design for manufacturability, really important in practice. Testability. So how well are you able to verify your design? Additionally, when the chip's being manufactured, when they want to test it when it's in the wafer to see if it's going to be viable and worth packaging, how easy to test? These are other things to consider. Or additionally, fault tolerance, right? How robust is your thing? Sometimes some applications, you really care about fault tolerance, right? If this chip is going in a rocket, you don't want the rocket to blow up if something goes wrong, you're going to need more fault tolerance, right? So These are a bunch of metrics I can think of, but I'm curious. Anybody in the room have any metrics I did not put in this list that might matter for a hardware design project? What's not on this list? Yeah, designability sounds great, right? You can imagine if you're an executive who has a team, you're going to carry a lot. You're going to care a lot about the headcount it takes to implement the project, right? If it's a 5-person project versus a 100-person project, or a 2-month project versus a 2-year project, that matters to somebody. So yeah, that overall design complexity, overall designability, yeah, that's a good metric. Anything else? Yeah. Yeah, interface complexity, I think, is definitely important. Um, I think that might fall under usability, but I think it's the same spirit, right? I think you're actually right, where it's like, yes, we built this chip, but this chip is unable to be used or unable to be interfaced. That's not going to do any good. Um, what else? How about this course? There's one keyword I keep always pitching about. We want to build generators not only because they're flexible. What's the other thing we want to get out of generators? Reusable. Yeah, exactly, right? So you're only designed for one purpose. Maybe you can figure out a way to make your design more reasonable but for other things, right? So the reason why we're having this conversation is to make people aware of the fact that when you're designing a project, there's just a lot of metrics, right? There's a lot of concerns, right? And so we need a way to kind of navigate this space. But yeah, I think the suggestions were great. Um, cool. Okay, so uh, given some metrics, the question is how do you explore that space? Okay, so metrics let you evaluate a single point, right? But how do you even know what the points are, right? What's the design space, so to speak, right? And so with generators, we can often have many more design points much more easily, right? And maybe in some other languages, you have to spend a lot of time manually coding things to get more possibilities. We've learned a lot with generators between, not just parameters, but, functional programming, other tricks that have lots of internal changes. And so we can just have tons and tons of knobs, right? And so when it comes to parameters, right, for today's talk, I'm kind of breaking them into two categories, what I call external and internal parameters. And so the external parameters are ones that affect how the component behaves externally, how people view it and perceive it. For example, what size problem does it solve, right? Okay, how many ports does it have? These are external parameters, right? Is it pipelined? Um, then there's internal parameters, which are very much based on the implementation rather than the external behavior, right? Things about like how architecture I chose to use internally, how parallel it is, how fast it is, etc. And so depending on the problem you're solving and depending on generator you're doing for your project, some of these other things may come up, right? Cool. Okay. So given these parameters, how do you go about actually exploring a design space? Well, uh, I recommend starting with a list of metrics and then kind of determining which ones matter. And even though we made a list of 8 and then we added a couple more, got perhaps more than 10, uh, it's pretty hard to design a project with 10 metrics, right? So you have to figure out which are your metrics, right? And so going through each of those metrics, figure out which ones matter. Maybe some of them don't matter. Other metrics may be ones that you really care about. Some are ones you care less about, so you maybe de-emphasize them, deprioritize them. Others may be metrics that aren't so much metrics, as more you can turn into a constraint. For example, this thing needs to go into a handheld device, so I don't want the power to be the power to be below 1 watt and burn someone's hand, for example, if you want to have some sort of limit. Um, so somehow you kind of try to prioritize and simplify your metrics, get down to a handful of, only a couple metrics you're trying to optimize, other metrics you've turned into constraints, and other metrics you're going to ignore. But the ones that are remaining, like I said, you're going to have trade-offs, right? You can't just win, right? You have 3 metrics at once you want to optimize. It's hard to improve all 3 at the same time, right? You're going to improve one at the expense of the other 2. And so those are trade-offs, right? Okay, so that's given just making sense of your goals and the metrics. But then when it comes to design space itself, um, we have a bunch of parameters, right? And so you have generators, you have all these knobs. You take the product of all the possibilities, you may have a very large number of possibilities, right? You may have thousands, millions, uncountable number of possibilities, right? In which case, you can't necessarily evaluate every design possibility, right? Um, and so it's worth kind of looking at that and identifying ways to once again try to tame this complexity, right? It may turn out that some parameters are actually really, really independent, right? So you can change one parameter and has basically zero impact in the implications of the other parameter. So as a result, rather than having, design spaces it's a product of two parameter spaces, one parameter has 5 options, another parameter has 5 options. Rather than having 25 possibilities to consider, you only consider 5 of each, right? And you consider 5 of this one, 5 of this one's 10, right? So you can kind of shrink things down, finding out what's independent. You may find some metrics, some parameters need to be paired together. And so even those independent parameters, they really should be one parameter. For example, matching throughputs between components, they should be matched, right? You also may find some parameters are really, really important. Like this is going to be a huge constraint, like how many ALUs I have. There's other ones, maybe not very impactful. Like, okay, this is some tiny little buffer in the middle of my design. If I change the size of it, it's going to have only a few % impact on performance, right? So like you can kind of get a sense for this kind of things. And so trying to just get a handle on this early on. This is part of what's beneficial by having an agile process is that you can start just trying things out, right? So you can't do every design point, but if you can start getting some information early, you can start learning about your problem and start learning things like, what? These parameters are really independent, or just parameters have very little impact. And you start learning those things from doing that kind of that early closing the loop. Cool. Okay, so then we've set our metrics, we've tamed design space, but at the end of the day, there's still some design space to explore. And so I'm giving some very general advice here, but this is very much application and problem dependent. If you think about what you're trying to do here, you have all these parameter combinations, and you have metrics, and so that's an optimization problem. In practice, these parameters you try and map to some n-dimensional space or whatever, you recognize as non-convex, right? So non-convex optimization. Guess what? It's an entire field of research on this, right? And so you do what you can to try to not fully encounter that problem, but sometimes you kind of have to. And so depending on the parameter space, trying every possibility is usually not possible. Brute force, you can't usually do, right? If you have millions of possible designs, you can't do that, right? And so what can you do? Well, this is where it gets really design specific. So there's some classic approaches to this. Some algorithms may have learned in theory class, like branch and bounds, and programming, randomized search, simulated annealing is one of these kind of approaches, right? It's kind of a way to explore design space. You may not get something that's perfectly optimum. You might get something that's pretty good in a pretty reasonable amount of time if you're lucky. Alternatively, there's been lots of research on this problem for years about what can we do, and some people actually have done things that actually try to mimic selection processes of evolution. Some of you may have been thinking, oh wait, I said non-convex optimization. Isn't that like what machine learning does? It is what machine learning does, and perhaps in a few years this will be better automated. There's a lot of different kinds of stuff, and so depending on the problem, you may find different types of exploration algorithms work better. For a lot of hardware design problems, you'd be surprised where having a few implementations and some human intuition and then kind of trying things out, you often can learn things pretty quickly. Like, oh wait, like this architecture is better under these conditions, and this architecture is better under these conditions. And well, which one am I under? Well, I guess I'm under this one. So you pick this architecture, and then kind of from there you can kind of start tuning the parameters, right? And maybe you tune some parameters first by trying different options, seeing how they perform, and then tune other parameters second, and kind of keep going from there. And so, okay, so however you do this, right? At some point, you're going to have a lot of parameters, a lot of design points you still want to evaluate. And the question is, how do you go ahead and evaluate these? Well, with this class, we're kind of pitching this philosophy of, make tools do the work, right? Set your chisel parameters up, generate Verilog, pass off the tool chain, and let it run. And if you want to do 100 designs, you do 100 designs, you put a cluster to work overnight, right? That's a lot of cycles. So what's the alternative? The alternative is to say, what if I explore a lot of design possibilities without actually writing the generators, use some sort of analytic model. And so this can be okay. So people can build these models that can, given design parameters, try to predict how well it would do. And so if you want to do a really quick exploration of a very large design space, sometimes models are great. They kind of get a sense for regions of interest, and then perhaps within the region of interest, you can go ahead and actually run the generators and actually do things, right? And so I would say prior to generators becoming widespreadly used, people did a lot of modeling work and a lot of stuff. People, job at Intel spend tons of time with spreadsheets trying to predict how some processor architectural changes have, performance on spec, right? They spent years doing that and they're really good at it. Um, but I mean, that's one option, right? The other option is to actually, if you have a generator, to actually just push it through a tool, see what it's actually going to do. And so they both have their merits, right? In this class, we're really pitching a generator approach, but that's good to get very high confidence in your numbers. But if you have a really big design space, sometimes models are still great to kind of get that first pass to understand what's even reasonable or feasible, and then you go in and run the generators. Cool. Questions? Okay. So let's talk about a hypothetical problem. Let's say, like you did in your last homework, you're building a matrix multiplication unit, right? Okay, so to get some, feelings of these numbers, what might you come across, right? Okay, well, first off, what size matrix am I solving? Am I solving a 100 by 100 matrix? Or am I solving a million by million matrix, right? Those are very different domains, right? 100 by 100, you might be able to do that completely all at once in one go. A million by million, that's so big you need a cluster, right? And so, what are you doing, right? And then, okay, let's say someone tells you, oh yeah, I want you to solve matrix 128 by 128. Is it always going to be 128 by 128? Is there going to be changes as parameters? Is it going to be smaller, bigger, et cetera? So you really want to kind of specify that problem. And then also realize your performance knobs. Okay, what's my performance target? Am I trying to do this, in as few cycles as possible? Or am I trying to do this, in however much time it takes? And so you can imagine it's kind of these very external knobs we'll have, for example, for performance, for interfacing, is it, how's the matrix fed in? How's the matrix fed out, et cetera. Then, of course, these are internal parameters, right? Things like how you're doing this architecturally, right? You're doing one dimension at a time, or you're doing 2 dimensions at a time, or you're doing some sort of systolic array, or some sort of other architecture internally. For matrix multiplication, in addition to ALUs, you're very concerned about your various uses of memories, right? How you're using on-chip memories, using off-chip memories, how you're arranging and buffering stuff, right? There's a lot of choices there, and you can imagine, depending how you designed your accelerator, you have a lot of different knobs to turn there. And then at the end of the day, what are your metrics, right? Here I've mentioned PPA as kind of the one. We talked about this, 5 slides ago. There's like 10 metrics, right? So what matters, right? And so you can imagine, for hypothetical design, if someone tells you, oh yes, I want an accelerator that does 128 by 128 matrix. They're 8-bit data types. So that one, maybe you can say, I can use, maybe do they're completely on chip. You do one design. Someone comes to you and says, no, I don't want that. I want, 1,000 by 1,000, and I want you to do, as many of those problems in parallel. Well, then maybe something kind of more GPU-like and bigger, and use off-chip memory, et cetera, right? So the problem constraints are really going to kind of shift you, right? And it's going to change what the right answer is. So sometimes the right answer for one size problem may not be the right answer for something else. Or it's the same problem, but the constraints change, right? I have more or less area, more or less power, and you might make different choices. So because of that, you need to explore at design space to understand what your trade-offs are and what makes sense. So let's say you're actually been given this task, right? So in the past page, I tried to, enumerate the problem, but what's actually happening? Well, if you're going to do this, you're going to first try to enumerate the problem, understand what your constraints are, what your goals are, what your metrics are, understand your resources. I recommend using n-leg model. And by n-leg, I mean really simple. Like think like back of the envelope, kind of on paper, scribbling, or maybe a spreadsheet, just to see what's possible, right? Okay, if I'm doing a million by million matrix, I should multiply those two numbers together and realize, oh wait, that's 10 to the 12, a quadrillion elements. Okay, I don't think I can fit a quadrillion elements on chip. I'm gonna need off-chip memory, right? I'm gonna need a lot of off-chip memory. I'm gonna need like a cluster, right? So you can kind of, yes, this is kind of the parameters. I did some math. Okay, I actually only need, 1 megabyte. 1 megabyte? Well, 1 megabyte could fit on chip. It could also be off chip, depending on how you want to do things, right? So you can kind of see, so do some early numbers to get a sense for like, just where am I in design space at all, right? And then based on that, you start thinking about plausible architectures. Okay, my design is gonna be purely on chip. I can do this with SRAM. I have, X millimeters squared of budget of area to build logic. Okay, well, perhaps I'll do this in a 1D architecture and try it out. So you say 1D maybe is your most promising architecture, implement that, get it working, get some numbers, get a harness to get some numbers out of it. And then actually, change some parameters, see how it changes performance, and see if you learn anything from that. You probably will. And based on that, you can say, what, maybe I can, make this thing more efficient here, make this thing more efficient there, and kind of tweak that architecture. Or maybe you might realize, what, despite doing all these parameters, maybe I'm not using all my area, and maybe I should consider architecture as more area intensive, and maybe I can do this whole process again. And you kind of keep repeating this, right? And what's nice about Agile processes, if you're doing this correctly, the more times you repeat 4 through 7, the better your design gets. But if someone stops you early, there should still be design. It's not I had a really great design or nothing, right? There's actually it's okay design, hopefully becomes a good design, hopefully becomes a great design, right? That's kind of the point, where to kind of incrementally keep improving. Cool. Questions? Okay, well then, I keep hyping up trade-offs. Let's talk about how we actually evaluate trade-offs. This is one concept that's like a general engineering concept. I love teaching this course. I don't think a lot of engineering students are familiar with this. This notion of a Pareto Frontier or Pareto optimality. So if you have multiple metrics you're trying to optimize, like I said, it's rare that one thing is uniformly better. Usually it gets better at one metric by being worse at second metric. And so in this particular diagram, we're considering two metrics. In this case, it's very abstract, X and Y. And so let's say in this case for today, we want lower is better for both metrics, right? So we want to be over here. Guess what? There's no points here. So this is many different designs, and we aren't there. So for example, if we compare these 2 points, we see that, okay, they have comparable metric Y. This one's to the left, it's lower, meaning it has better metric X, right? So guess what? If you had to choose between these 2 points, you would pick this one because it's better at metric X. Likewise, if I compare some points in the vertical direction, like these 2 points, okay, this one, for the same X metric, I can get a lower Y metric. So this one's better, right? What's interesting is there's these green points I've highlighted. These are what we call Pareto optimal points, meaning that if I'm this point, nobody's going to be better on X without being worse at Y, or better at Y. Sorry, I'm getting my directions mixed up. Oh no, it is worse at Y. Sorry, so right. So lower is better for both, right? So if I'm this point, in order to do better at X, I have to get worse at Y. If I want to do better at Y, I have to give up on X, right? That's kind of the point. And so this Pareto optimality, this notion, as I said, it's kind of appreciating the fact that there's this frontier right here, right? And so points are on the Pareto optimal. This is the Pareto frontier, and like I said, you want to be considering points on this curve, right? If you're over here, it's possible that if you change your parameters enough or change your architecture enough, all of a sudden you have a design that's better at everything. When you find yourself forced to make trade-offs, that's when you know it's the frontier. And what's interesting is I drew the shape. In this case, this is me drawing this in an image program. This shape emerges all the time with actual real data. Because this happens, right? In real engineering, right? When you're really pushing the frontier, you have to improve one to get to the other, right? There's really going to be trade-offs. Like I said, so you can improve one without any consequences. That means you're somewhere over here, right? If you're just going from here to here, you're not on the frontier. Okay, so from examples, how about this one? So this is a plot from a paper, and what's interesting about it is number one is matrix multiplication, like we just talked about. So you can see there's a zillion design points they considered, right? They considered so many design points. And what's amazing is that in this case, they have two metrics they're considering, power and performance. This is time. So for both, lower is better. The same curved shape emerges, right? It often emerges. So you can see that, you want to be picking designs along this edge, right? If you're over here, wow, you could, save a lot of power or go a lot faster for that budget, right? But yeah, if you're over here, to improve one of those metrics, you gotta give up the other metric, right? So you want to be on this frontier. Now, one of the challenges you have when you try to visualize this kind of data is that if you have a zillion design points and a lot of parameters being swept, there's only so many colors and shapes you can color points, right? And so it's kind of hard to convey all these points. And so sometimes there's a little bit of work to try to kind of piece it apart. So the author of this paper, who's now a professor at Berkeley, Sophia Shao, she tried her best to annotate this diagram, kind of telling you what's happening, right? So for example, as she's suggesting here, right, as you increase the size of your L1, you can really improve performance. But a larger L1 cache is going to be more SRAM, more power, and that's why the power is shooting up. But guess what? That can really improve performance because guess what? You're going off chip less, right? Some of these other colors are showing the bandwidth. There's additional properties over here. So you can see, for example, that depending on what you're changing, there's various trade-offs. But you see this Pareto optimal shape here, right? So you should be familiar with the fact, okay, if I'm on the frontier, I'm getting here. And so guess what? If I do only some of these experiments, let's say I was only doing the orange color experiment, there's some amount of that curvature to this. But actually, the orange design, for example, is typically not your Pareto optimal one unless you really, 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 really want to push performance. Okay, then orange is the best one. But otherwise, you probably shouldn't pick orange. You see which colors on the edge on the frontier, and this is why they chose the color pattern they did. It changes, right? Here it's orange, here it's yellow, here it's green, here's the other green. Maybe it's brown a little bit, and it's the other blue. So you see, this is why you have design inspirations. You really want to see what are all the possibilities, what are all the options, what are all the parameters, and explore this. And so if you're only doing like 2 or 3 design points, you aren't getting this, right? You aren't learning how close you are to the edges. You aren't knowing what the limits are, how much you can push it, right? And so you really want to have a lot of design points in your exploration to figure this out. Now, for context, you may be wondering how this particular offer has so many freaking design points. There's a lot, there's hundreds out here. Uh, the research paper is actually called Aladdin, and the contribution actually was a methodology to build up pretty good models for designs. So rather than pushing it all the way through the tools, this actually is a model that considers a lot of physical costs pretty well. It's characterized based on your self-technology library you're using, and based on that, can try it analytically with very high resolution models explore design space for you. But whether you're using models or actually pushing things through the tools, you want to have a lot of design points to see what's going on. Now, for most projects in this course, I don't think you're gonna have enough knowledge to make this many points. This is probably the most rich design space plot I've seen shared publicly, so don't feel too bad looking at this one. But when you have the ability to do design exploration, you do want to get a lot of points, and you want to see this shape emerge, and it usually emerges when you actually do the exploration. Cool. Questions? Um, we have one more of these. This is from another paper. This one's a more sane size design explorations. They're looking at uh, processor designs, and they were changing various parameters. In this case, they actually had a few different processor designs. You can see them listed. There's 6 of them, right? Either in order, out of order, 1 wide, 2 wide, 4 wide. And then they were changing the frequency, right? And because they're changing the frequency, they were also able to change the voltage, and this they were able to get different energy points. So you see, for example, like, maybe we can take this one down here. This is the dotted line, brown circles. That's a 1 wide in order processor, maybe perhaps even 5 stages for a classic one like the class. You see that, yeah, if you want to improve performance, so that's, to the right is better, it's going to cost you more energy per instruction. So in this case, they've normalized it per instruction, but you see that, oh yeah, you're increasing the frequency, you're increasing the voltage is squared, you're paying a premium. So eventually, for a long time it's linear, eventually that quadratic gets you and it gets expensive. And so once again, you can see that by considering 600 processor designs, they get a much more rich design space here, right? If they only consider one processor design, yeah, they can see that trade-off. There's a trade-off there. That's just sweeping parameter on one design. And by sweeping multiple designs, they can kind of see where these benefits are, right? And so once again, we want to trace the underside of this curve to kind of find that Pareto frontier. You see that depending on what performance target you have, a different architecture is going to be better. And you can see that in this case, most architectures they considered actually had a regime in which they were the most efficient. And at some point, they're not the best ones. So if you want to go really low performance, guess what? In order 1 wide is going to cost you the least power, so you might as well do it, right? But eventually, in order to get a performance, rather than having a really high frequency 1 wide, it's better to have a lower frequency 2 wide, right? And they find that, okay, and then at some point, there's a tiny regime over here where, if you want to go faster still, rather than having a really high frequency 2 wide, it's better to have a lower frequency 4 wide, for example. And at some point, you know what? Out of order is better. So you should look at an out of order 2 wide, or perhaps even an out of order 4 wide. And you may say, what happened to out of order 1 wide? Well, that is this one. And that point seems to never win out, right? So in this case, it's never the best, right? But some of these other points, like, this point labeled D3 right here, that is Pareto superior, right? Based on designs considered in this experiment so far, if you want to improve performance, you need to pay more energy. Or if you want to reduce energy, you need to accept less performance, right? So you can kind of see this. So you really want to kind of be attacking or exploring this Pareto frontier. And so I think some people from this room, for example, spend their time optimizing SRAM for Open RAM, and I'm sure you can make plots like this if you try enough parameters, right? If you could. I'm seeing head shaking, but you could. Maybe I'm going to inspire a paper here, right? change your voltage, change your architectures, change your, your array dimensions, change how many bits you have per mat, change your decoder design. This is doable. This could be done. It could be done, right? And you can see, you know what? For, if I have a, 256-bit mat versus a 512-bit mat, 128-bit mat, you see which one comes up with certain parameters. And so you can get this. And so if you can get enough points, these curves emerge. And usually if you don't have a curve and it's more of a point cloud, which don't worry, I've been in research projects since this happens, that usually means you have enough points. And you figure out a way to get more points, and all of a sudden that point cloud gives you this familiar curve shape. Cool. Questions? Well, that's all for us. I'll see you all on Monday. Have a good weekend.